I would like to introduce our today's speaker, Vladimir Djordjic. He is a PhD student in University RWTH Aachen University, and also at University of Novi Sad. He's gonna talk about moment equations for a polytropic gas reproducing adjustable transport coefficients. So please, Vladimir, the stage is yours.
Thank you very much. Good afternoon to everyone. Can you hear me? I suppose
yes,
that
we can hear you.
Okay, nice. I will share my slides. Okay, let's start. So yeah, today we will talk about moment equation for polytropic gas, and this is actually done with collaboration with Milana Djordjic and my advisors, Manuel Torion and Nicolas Pasevich. And we are supported by COST and DFG. So let's start. So this is the outline of today's talk. And first, assuming that you don't have any knowledge about Boltzmann equation and so on, I will first talk about a little bit about Boltzmann equation for monatomic gas, and then we will switch for topic, and that is polyatomic and more precisely polytropic gases. And actually, there we will consider what is the form of a collision operator for polyatomic gases. And then we'll look in some system of equation, actually a system of 40 moments and 70 moment equations. And yeah, let's start. So first, a main tool in kinetic theory is distribution function, and this idea came from Boltzmann, and instead of tracking position and velocity of all particles, you introduce a distribution function f that depends on the time, position, and velocity, such that f times dx dv represent a number of molecules in this differential, let's say, box dx dv at time t, and then the derivation of the changing of distribution function is represented by a Boltzmann equation, and it consists of two parts. Actually, three parts. The first part is a time derivative, and second part is transport derivative of f. And on the right hand side, you have collision operator, and the function of this collision operator is to take main goal of this collision operator is to take care about collision. So assuming that actually collision happens only between two particles, so we have two particles or two monatomic molecules that are colliding, and we know that before the collision they have some velocities v prime and v, and after collision this change to the particles have new velocities v star and v, and this collision operator actually counting how the velocity of the particles is changed, meaning that how you can get new particles. So when you collide particles with velocity v prime and v star prime, then as an outcome you have a new particle with velocity v, but you can also lose the particles in opposite, like in collision in opposite direction. That happens, and actually this term actually caring about that. And you also have cross section, be that tells you somehow like intensity of these collisions, and you integrating over all possible combination of velocities of collision partners. So main idea in next step actually is to reduce this integration area by looking actually what is the law during the collision of these particles. And we have two collision laws. First is collision law of momentum, and second is collision of conservation law of momentum, conservation law of energy. So I say that if you introduce reference relative velocity and velocity of center mass, it says that velocity of center of mass does not change, and also the reference, the intensity of relative velocity also remain the same. So here actually we have integration over 3D if our velocity if d is the dimension of velocity, and then obviously we have d plus 1 equation, so we also need some parameters like and then here's come like sigma that come from unit sphere. And how it works, so you choose some velocity, and then you found the center of mass and relative velocity, and we know that this will not change after collision, and you choose some arbitrary vector sigma that come from unit sphere, and then you know that this pre-collisional velocities will lie on the circle because this the relative velocity, intensity of relative velocity is conserved, and also the center of mass also remain the same. So this is actually the picture. And this equation helps you to reduce integration on the collision operator. And this is how it looks like now. So notice that here you integrate only over the sigma and one velocity. And in monatomic situation, usually for a cross section, we choose hard-sphere model. So the cross section is proportional to relative velocity to some power and times some function of angle that in most application actually is constant. And then comes the situation with polyatomic gas. So why this is specific? It's because your molecules have more richer structure, and then during the collision, your molecule can rotate, your molecules can vibrate, and all of this actually reflects of energy of the molecules. So we will introduce another microscopic quantities beyond the velocities, and it say that it's called microscopic internal energy. And now this variable also becomes goes in distribution function such that f times dx di represent the number density of the particles in these intervals. So another interesting fact actually is that distribution function is changing because obviously it depends on a new variable, and here I plotted how it looks like. So you can see that in the velocity space, it's very nice curve. The goddess of all curves looks like Gaussian, and in internal energy space, it looks like that. I don't know, some not quadratic, like root function, let's say. And here you can notice there is also one parameter is called delta, and delta is related to degree of freedom of molecule. So depends what is structure of your molecules. This delta is related to that, and also it can be related to adiabatic coefficient. And again, to model polyatomic gases, again, we will use our favorite and main tool, Boltzmann equations. And the funny thing is now we also have to adjust our collision operator, and we'll do it on the same like before, by looking first. Let's say look at how the conservation of momentum and conservation of energy looks like. And you can see that actually conservation of momentum remained the same, but conservation of energy is changing because we also consider internal energy of the molecules. And same like before, introducing the center of mass velocity and relative velocity, you can write this in this form. And then again, we want to reduce the space of integration, and we, in a similar way, we conclude we need D+1 parameter. And as before, sigma will be our standard parameter, but we need two more. And for that two, Brunakle and Larsen suggest that this way. So first parameter, capital R, will split our energy, our pre-collision energy to two parts. First part is the kinetic energy, and second one is internal energy. And then we also introduce a new parameter R, small r, such that we will distribute the energy between these, between two molecules, basically. And then in the same way, our aim is to express this pre-collisional velocity in a function of post-collisional ones. And now situation is a bit different because you notice that you can notice that comparing to monoatomic case, in polyatomic case, this will not be in this circle. So this kinetic, let's say relative velocity is not conserved because energy can go to the internal energy of the particles. And when you put that all in this collision operator, this is how it looked like. And another problem is that we need to think about what actually should be the cross section, because in monatomic case it's very let's say simple. We just choose a relative velocity to some power. But now we want two things. First thing is we want our cross section to be microreversible. And what microreversibility means, it means that if you change the collision partners, so if you change post and pro collisional velocities and internal energy, these cross sections should remain the same. And in the work of Gamba and Pavic-Djordjic, they suggest this form of the cross section, and this form actually is geometric mean between post and pre collisional quantities. And very important thing is that for this cross section, you can prove existence a uniqueness of Cauchy problem for homogeneous Boltzmann equation. So we are motivated to use this cross section, and we will continue with this form of cross section. So another important thing is that my measure is, when I choose, actually my measure is cross section multiplied with this factor, and we want this factor to be invariant between invariant to the change of pressed pro collisional velocities. And why we want this? So we want this because the station, when we multiply our cross section with some test function, and then after integration, we want to calculate this. So, and this invariance allows us to play with measure and to have form like this. And you can notice that for a specific choice of this test function, this term here, this difference become a 0. And actually, this test function actually comes to how you can find this. You can look in your collisional laws. So you know that from collisional momentum, you know this will be conserved, and also energy will be conserved. And obviously, these functions are very funny because only by multiplying and integrating from right-hand side, it will become 0. So this is very nice situation. Actually, motivates us to see what will be situation when you multiply your Boltzmann equation with this and integrate. And first step is actually to look what is the left-hand side, or what happens when we multiply our distribution function with some test function and what it's get. So, and this is very nice because it gives you information about density, about velocity and pressure inside you gas. So this actually, our distribution function is very rich function because it carries information about all variables that we want. For example, and then beyond all of these variables, we can also have some new variables like dynamical pressure that are new comparing the monoatomic gas. And also you can look what is the stress, and also you can look what is the heat flux inside your gas. And we can also, and in future talk, I will split this heat flux into 2 parts. One heat flux will be translational heat flux, and another one will be internal heat flux. So I will stop a little bit now and ask you, do you have questions? Okay. If not, let's continue. Yeah, about the weak form. So, as I said before, multiplying by collision operator by some test function and integrating, you can obtain the moment equation or transitional equation. So, and how it works? So you multiply whole Boltzmann equation with test function and then integrating over this space dv di, and then you can notice actually that it has very nice structure, because if you for next, let's say in this step, you choose this function, C alpha, and then if your next step or for a next step test function, if you choose velocity times same text function, this quantity actually is the flux from previous equation. And you can continue this process to the infinity. So moment equation actually have very nice and hierarchical structure. And always the question is, okay, at some, after choosing, let's say 10 text function, I want to stop. And then always you have one flux that is unknown. So we have high order fluxes, and we have to close this system if we want to work with this system future. So how to close the system? And there is some suggested closure like Rad closure or maximum entropy principle. So, and at the end, so when you know how what is distribution function, what is the form of distribution function, this is how in general moment equation system looks like. So you have derivative plus divergence of the flux, and on the right hand side you have production terms. And let's try with some test function, for example. Let's try with 14 moments distribution function. And first, how the distribution function looks like. The graph assumes that this is like expansion about some coefficient times our test function and times already mentioned function or Maxwellian, the function equilibrium, such that it satisfies our requirements for the moment. So we require of a distribution function that m times distribution function should give us density, and then if you choose m times this is relative velocity, then it should go 0, and then this will give us density. No, sorry, the pressure. This will gives the combination of the pressure and dynamical pressure. This will give heat flux and so on. And you can notice that actually in this distribution function, all the quantities appear. So all these quantities appear in this distribution function. So when you multiply distribution function with some test function, so you're doing like something like projection, these quantities again goes to the moment equation. So a little bit looks like a going in circle, but it is not. And yeah, and in some case, your right-hand side, speaking your right-hand side or production terms, it will not be 0. So we know that for a specific function, this will be 0, like if you choose velocity or total energy or only 1 or mass, this will give you a 0. But for this red colored test function, you will have something on the right-hand side that is non-zero. And then we have to compute that. And if you're doing this by hand, it's very long, and yeah, it requires some knowledge and computation skills. But we made some very small mathematical notebook, and by simply choosing this test function, you can easily evaluate these production terms. Actually, more the code evaluates these coefficients. And then this is how the right-hand side looks like. So you have some production of, for example, equation for a stress. You have some production of stress and dynamical pressure, and an equation for a total heat flux. Again, you have some production. And okay, now we have moment equation system, and what we can do with that. So first, we can compare with physical properties of gas, such as, for example, Prandtl number. And from this coefficient, you can extract your shear viscosity and heat conductivity. And from that, you can compute a Prandtl number, which is a ratio of these two. And this Prandtl number is very common in physics. There's also experimental data for these values, but there is also another relation that actually connects the degrees of the freedom of molecules and the Prandtl number. And depends on actually how your molecule looks like. If it's linear molecule, like for example, N2 is linear molecule, then we will choose delta to be equal to. And if some nonlinear molecule, we will choose, let's say, delta is equal to 3 and so on. So this is actually known, and this Prandtl is function of delta. And this Prandtl also is function of delta, and also some psi. And this psi can be found from temperature dependence of heat of shear viscosity. So this can be extracted from data. And on the next slide, I plotted this for some values of psi. And you can see that actually this is good. I mean, up to the 11%. And you see that this this green dashed curve is Eucken, and this one is a Prandtl number from our moment theory. So this is good if you're satisfied with this arrow. This is fine, but the question is, can we prove this? And answer is yes, but we need a little bit to adjust our cross section. So, and speaking of that, we introduce the collision in which internal energy will not change. So this is our collision where internal energy is fixed, and then in such collision, also your relative velocity remains the same, and parameterization is basically the same like in monatomic case. So for this, let's say we can introduce new collision operator for especially for these frozen collisions, and with some cross section for this collision. And this cross section can be seen like our standard cross section, or this operator can be seen as a standard Boltzmann collision operator for polyatomic gases, but with this delta operator multiplied by cross section. And summing all of these, we will use our standard collision operator and also frozen collision operator, and also we add some weight omega, and omega goes to 0 to 1. So how this omega says how much the frozen collision you want, how much no frozen collision you want. And as I said before, this also actually can be seen as one operator with this form of cross section. And we will add a little bit more freedom by adding new parameter eta in cross section. This will also satisfy the microreversibility and uniqueness theory. And we also introduce this factor that have a purpose to give consistency with case when the cross section is choose like Hartsfield model, so like monatomic case. And then in frozen part, we will also exchange this eta to the eta frozen. So now we have a lot of parameters, and these parameters actually are very useful because then you can adjust your coefficient. But also another important thing is to increase the number of moments. So first, we will increase the number of moments by splitting the heat flux into two parts. One is translational heat flux, and second one is internal heat flux. And this is how the distribution looks like. And this, when you plug this and project this gives moment equation system. And here I only extract the equation for stress and for these two heat flux. And this equation is linearized, and I consider only the linear high leading order terms. And from these two equations, we can extract heat conductivity, and from this equation, we can extract shear viscosity. And important thing that thanks to this factor, all this coefficient goes to its value like in monatomic Hartsfield model. And here actually, when you solve this, so you can extract what is from this equation, you can extract what is shear viscosity and heat conductivity, and then you can compute the Prandtl. And in a special case, when omega is equal, eta frozen is equal 0, this will give like slightly improvements of Eucken relations. And here I plotted this Prandtl number for a different value of zeta over delta. And also for different parameters of omega, which is ratio between frozen and frozen collisions, and eta frozen. So you can see that actually this model can give you infinitely many Prandtl curves, and basically adjusting this parameter for each delta, you can precisely find parameters such that you are very close to the oiken. And moreover, actually, if you look into experimental data, then you also can try to find these parameters such that you are very good to the experimental data. And this yellow curve, actually yellow area, represent all possible value that where actually your curve can be. And another important point is that how many moments system we need such that we can approximate this very nicely. And here I do everything like before, but I choose the 14 moment system and I plot these curves. And you see, for example, for small parameters, for small value of zeta that correspond to temperature exponent of shear viscosity, you can see that this area is smaller comparing the 70 moment range. And in this case, for example, you cannot find very precise the value for oiken. So we need more moments, and this is like very small justification why the larger moment system are better. Yeah, in principle, should be like more moments. You have more information of your system, and you can more precise the modeling your figures. And here I'll come to the end. And first, what we can look future. So we have our moment equation system. We can adding some boundary condition, and we can look in some process simulation like heat conduction or for polytropic gases, or for example, lead-driven cavity problems and so on. So also, thanks to this code, we can also produce coefficient for higher order moment system. And idea is also to examine what is actually influence of this high moment system comparing the smaller one. And some plan is actually for the future to work also with mixture of polyatomic gases. And we're also looking for a comparison with semi-classical approach where this internal energy is discrete function. So, and yeah, this is some plans for the future. Okay, thank you for your attention, and yeah, please step out if you have with question.